Hello everyone, welcome back to Z Physics. Today we're going to be solving the engineering assessment for Cambridge University. This is the sample 2020 paper, and in this video I'm going to be going over the physics questions only. Just a little note, a little disclaimer that these are not official solutions, they're just my solutions. So if you come across something that can be solved in an easier way, or if you spot a mistake, please do get in touch. Okay, well, let's get started with question 1. So we have a soldering iron which has a copper tip of a mass 2 grams. The tip is heated with 30 watts of thermal power. In 50 seconds, the temperature of the tip increases by 200 degrees C. How much energy is transferred from the tip to the surroundings in this time? And we're given the specific heat capacity of copper. Okay, well, because we're looking at essentially how much energy is lost, we're going to need to compare the electrical energy to the energy that has actually gone into the soldering. So first off, the electrical energy, because power is energy over time, this means that energy will be power multiplied by time, which is going to be 30 watts in 50 seconds. That's going to give us 1,500 joules. So in a way, this is our input power. Now, so let's just call that E1 or something like that. Our output power will be given by E is equal to MC delta theta, the specific heat capacity equation. Okay, well, let's figure this out. So this is going to be the mass, which is 2 grams, converted into kilograms. It's going to be 2 times 10 to the power of minus 3, times the specific heat capacity, which is 400, times the change in temperature. By theta, I normally put in any quantities or any temperature which is measured in degrees C, by the way. So 400 times 200. Okay, so this over here is going to be 2 times 400 times 200 times 10 to the power of minus 3. So it's going to be 160 joules. Okay, now you can see that there's going to be a lot of energy lost into the surroundings. Our electrical energy is 1,500, take away 160, and we're going to get 1340 joules, i.e. a correct answer being C. Okay, skipping to the next physics question. Question 3, you have uranium-238 decays by a series of alpha and beta emissions to become the stable isotope lead-206, and that's 20682. How many beta particles are emitted in decay of one uranium-238 to lead-206? Okay, well, let's think about it. First off, our first clue is that the only process that affects the nucleon number, remember this number up here is the number of protons plus the number of neutrons. The only process that affects it is alpha decay. Now, every time we have alpha decay, let me just write this over here, we actually have an emission of an alpha particle. So it's an emission of the alpha particle, which is just a helium nucleus with 2 protons and 2 neutrons, so overall 4 nucleons up here. Okay, well, if we've gone from 238 to 206, well, that's a difference of 32, isn't it? So that will be a difference of 32 nucleons. With each alpha decay, we're actually dropping 4 nucleons because the nucleus, well, an alpha particle escapes away from it, and each alpha particle is carrying 4 of those and 2 of those. So let's just divide by 4, and this means that this would have had to have been done 8 times. So that would be 8 alpha decays that we can write in like so. However, that's not the only thing that is happening. We also have beta decay. Now, if you're unsure about beta decay, I'm going to leave a link in the description on my video on beta plus and beta minus decay. However, in short, anytime we have beta decay, a neutron is turned into a proton. So as we are losing alpha particles and we are losing protons, we're also gaining, probably at a slightly slower rate, protons as well, because for our beta decay, a neutron is going to be turned into a proton. Now, how many exactly? Let's assume that there were no beta decays whatsoever. If that was the case, we would have had 8 alpha decays, and each of them would have lost us 2 protons. So that would have meant, so if there were only, if only alpha decay for 8 of them, you would lose 8 times 2, which is 16 protons. Well, let's have a look at the difference between the proton number. We have 92 here and 82 here. So the difference is 10. So this means that in order to have that difference of 16, we also needed 6 neutrons to have turned into protons. Therefore, the answer has got to be A. So next physics question, for question 5, we have a DC electricity transmission systems uses an undersea cable to send electricity from one country to another. On a particular day, the first country supplies electricity at a voltage of 400 kilovolts, it's high voltage, and 2000 amps. The second country receives electricity from the transmission system at 160 kilovolts and 4000 amps. What is the percentage efficiency? Okay, well, let's calculate our input power. So I'm just going to write over here that this here is our input power, and we'll just use P is equal to VI for this. Now voltage is 400 times 10 to the 3 multiplied by 2000, which is just 2.0 times 10 to the 3, and this will be equal to 8 times 10 to the 6 times 10 to the 2, so it's going to be 8 times 10 to the 8. That will be watts, and this is our total input power. Our output power, which is the power that's been received, let's call it the output power. And let's just use P is equal to VI again. So P is equal to V times I. Now in this case we received 160 kilovolts. So that's 160 times 10 to the power of 3 times 4000, which is 4 times 10 to the power of 3, which is going to be 4 times 160 times 10 to the power of 6. And that's going to be about 6.4 times 10 to the power of 8 watts. Well, let's figure them out as a percentage. So let's say 6.4 times 10 to the 8 divided by 8 times 10 to the 8, that's just going to cancel, times 100. Well, that's just 80%. So we know that our answer is either going to be D, E, or F. Now, how much energy is wasted every minute? So this is kind of interesting. It's every minute. Okay, so how much power is actually wasted overall? So it's going to be 8.0 minus 6.4. So let's just say, I'm just going to write that over here. So the power wasted, that's going to be 8.0 minus 6.4, so that's 1.6 times 10 to the 8 watts. And we can figure out the energy. I'm just going to do that over here. So the energy is power times time, PT, which is our power, 1.6 times 10 to the power of 8 multiplied by the time, because we're talking about a minute, so that will be times 60, and multiply those out, we're going to get 9.6 times 10 to the power of 9. Correct answer is D. Okay guys, on to question 7. We have two fixed horizontal metal rails which are side by side 12 centimeters apart as shown, and they're connected to a DC power switch that is initially left open. We have a freely movable metal rod of length 20 centimeters is placed on the rails as shown in the diagram, and we have the angle between them is 90 degrees. The whole arrangement is placed in a uniform magnetic field of magnitude 0.5 Tesla that is directly perpendicular into the page. Okay, so we can use this notation just to illustrate this. 0.5 Teslas into the page. Okay, the switch is now closed, so let's draw the switch which is now closed, and as a result there's a 2.4 amps current in the circuit. So this means the current is kind of going to go through here, positive to negative, go down here and then across to here, and the size of the current is 2.4 amps. What is the initial magnitude of the acceleration of the rod, and what is the direction? Okay, well, this question is all about using F is equal to Bill sine theta. However, I'm just going to use F is equal to Bill because everything is perpendicular. There's definitely a catch though, and the catch, as you can see, is that not the entire rod is within the region where current will flow. Current is going to flow through here, then down here, and then across to here. And this region here will not be at all affected by the current, and hence there will not be a magnetic force from that region. So to calculate the value of the magnetic force, we can just use F is equal to Bill. So let's do that. I'm just going to write it down over here. F is equal to Bill. So the magnitude of the magnetic field, the magnetic flux density, is 0.50 Teslas multiplied by the current, which is 2.4 amps, multiplied by the length with current flowing through it, which is 12 centimeters. So it's going to be 0.12. Now let's put this into a calculator. I'm going to get 0.5 times 2.4 times, or use just mental maths if you are doing this exam. So it's going to be about 0.144 newtons. Okay, now to calculate the initial acceleration, we're going to need the mass, but luckily we already have the weight given. So just from this statement over here, we can figure out the mass pretty easily. So we know that the weight is equal to mg, therefore g will be the weight divided by the mass, so it's going to be 0.40. Oops, let's write this a little bit more carefully. So the mass will just be the weight divided by g, so it's going to be 0.40 divided by 10, like so. So it's going to be 0.04 kilograms. Okay, well, let's work out our acceleration, assuming that's the only force that's acting on the rod. So we're going to use F is equal to ma for that, and the acceleration will just be the magnitude of the magnetic force, 0.144 newtons, and then we are going to divide it by the mass, so it's going to be 0.04. and we are going to get 3.6 newtons. So the answer, looking at all of those answers, will either be E or F. Now, in order to determine the direction of that force, we need to use Fleming's left-hand rule. Divided by the mass, which is 0.04 kilograms, and this is equal to 3.6 meters per second squared. So this means the correct answer will either be E or F. Now, in order to determine the direction of this force, we're going to need to use Fleming's left-hand rule. Now, in Fleming's left-hand rule, remember our first finger, or the index finger, so the first finger or the index finger is the field, or the direction of the magnetic field. So this here is also known as our index finger. So we can do that in brackets. Our second finger is the current. Our second finger is the current, and our thumb gives us the direction of motion, which is the direction of the force. If we were to align our fingers so that our second finger is along here, and our first finger is sort of into the board, then we're going to see that the motion is actually to the right. So the force, the magnitude of the force will be to the right, or the direction of the force will be to the right. Therefore, the correct answer will be F. Okay, question 9. We have two trolleys which are moving towards each other along a straight horizontal track, as we've shown just here. One trolley has a mass of 8 kilograms and is traveling to the right at 4 meters per second. The other trolley has a mass of 2 kg and is traveling to the left at 1 meters per second. When they collide, they're going to stick together. How much kinetic energy is transferred to other forms in the collision? How much kinetic energy is actually lost in this inelastic collision? Well, let's first off calculate the initial kinetic energy. So I'm going to call that, I don't know, let's say KE1 or something like that. The initial kinetic energy will just be a half times the mass of the first one, so times 8, multiplied by V squared, so it's going to be 4 squared, plus a half mv squared again, so it's going to be a half, times the mass times v squared, which is just 1 squared. So let's do a little bit of simplification. So that's going to be 4 times 4 squared plus 1, and 4 squared is 16, times 4 is 64, plus another 1. It's going to be 65 joules of initial kinetic energy. Now, what will happen when the two objects they've essentially stuck together and they formed one object? It's going to have a mass of 8 plus 2, in other words 10 kilograms. In which direction will it actually be moving? In order to figure this out, we need to use conservation of momentum. So let's work out the conservation of momentum. So mass times velocity for the 8 kilogram mass, so that's going to be 4.0 times 8. I'm going to take the direction to the right to be positive, plus now 2 kg, and the 2 kg will be multiplied by 1 meters per second in the opposite direction, so it's going to be 2 times minus 1. And this will be equal to the total momentum after the collision. So after they've stuck together, the total mass is going to be 10. And the velocity will be some unknown velocity. We're going to call that v, that we're going to find out now. So 4.0 times 8 will just give us 32. Minus 2 is equal to 10v. So it's going to be 30 divided by 10. 30 is equal to 10v. In other words, v will be equal to 3 meters per second. So that's plus 3 meters per second. So this means that the direction, the resultant velocity, is going to be to the right in terms of a direction. So to the right, just like that. Let's write it to the right over here. Okay, well, let's calculate the final kinetic energy now. Because our final kinetic energy, so let's call that kinetic energy 2. And that's going to be just a half times the mass, which is 10, multiplied by our final velocity squared. So it's going to be 3 squared, which will be 5 times 9, which is 45 joules. So we can see that initially we had 65 joules, now we have 45, which means that 20 joules has been lost. So the correct answer is C. Okay, next physics question, which is question 11. We have a car of mass 800 kg traveling in a straight line along a horizontal road. The car accelerates non-uniformly from rest for 5 seconds and then moves at constant speed as shown in this distance time graph. What is the average resultant force acting on the car of the time for which it is accelerating? Okay, well, the acceleration only occurs during this portion of the graph when the gradient is changing. As soon as it reaches this constant velocity, the car just kind of moves along with this constant velocity. We can actually work out this final speed of the acceleration simply by using the gradient. Okay, so the gradient of this graph, let's take points across here and here will just be, let's call that the final speed. That will just be 40, take away 10. And then on the x-axis will be 10 minus 5. So it's going to be 30 divided by 5, which is equal to just 6.0 meters per second. Okay, now that we have the final speed, we also have the initial speed. We could approximate the acceleration and hence approximate the average resultant force. So as we know, the acceleration is delta v, the rate of change of velocity over change in time. So our delta v, because it's going from 0 to 6 meters per second, then our change in speed will just be equal to 6.0 meters per second, and this happens in this time frame of 5. So this will be equal to 6 divided by 5, which is 1.2 meters per second squared of an acceleration, which means that the force, the average force that's been acting, the average force will just be the mass multiplied by the acceleration, and the mass is 800. So if you were to just multiply this by 800, it's going to be 800 times 1.2, which is 960 newtons, which means that the correct answer will be D. Okay folks, so we'll stop here for now. We'll solve the rest of the questions in a later video. Hopefully this has been useful. Thank you very much for watching, and I'll see you in the next video for the remainder of the questions.